Hello, so here we are starting chapter 4, and this is AP Chemistry. And in this chapter, we're going to be talking about solution stoichiometry. So we're going to talk about many different types of solutions and chemical reactions. We're going to be talking about precipitation reactions, acid-base reactions, and also redox reactions. So there's a lot of information in this chapter, so there's just a lot to know. All right, so let's get started. All right, so first we need to review what aqueous solutions are. So aqueous solutions are basically anything that's dissolved in water, okay? Remember, water is known as the universal solvent, okay? Solvent is what does the dissolving, or what we call the dissolving medium. So remember, we had these two terms, solute and solvent. So solute is what needs to be dissolved, and solvent is what does the dissolving. So in order to be classified as an aqueous solution, it is obviously going to be dissolved in water. So let's review our properties of water. If you remember, water has a bent shape. Okay, so that means like when we draw the Lewis dot structure, it has this bent shape. Okay, and also, let's see. So let me sketch it out, the Lewis dot structure. If you remember, so there's H, an O, and an H. And if you remember, there were these two lone pairs. Hold on, let's fix this O. So two lone pairs on the oxygen, so there are dots there, and there are dots there, okay? So then this would give it what we call that bent shape, okay? Either bent, or some people refer to it as a V shape. All right, also with water, remember, water is polar, okay? Polar. So then that means you have to go back and try to remember what polar means. All right? So polar means that it has poles. Okay? It has poles. And polarity is based on their difference in electronegativity values. So this is where you guys are like, oh my gosh, electronegativity, I remember the term, but I don't remember what it means. So electronegativity is the atom's ability to attract electrons to itself. So which atom or element is the most electronegative? So remember, this one is fluorine. Okay, fluorine is the most electronegative. So electronegativity is going to increase towards fluorine, and then it's going to decrease going down. Okay, so decrease going down. Decrease. All right, decrease going down. All right. So let's see. So if we take a look here, between this oxygen and the hydrogen, which one is more electronegative? Well, oxygen is. So that means that these electrons, okay, the electrons that they're sharing right here, they're going to hang out more towards the oxygen, okay, because the oxygen has a greater attraction for the electrons. So we say that the oxygen has what we call a slight, pen option, has a slight negative, okay, so let me write that. The symbol is this lowercase delta, the Greek letter delta, okay, so then it is a slight negative, and then this H is a slight positive, okay. So this little slight sign should be a little more curved at the top here. It's not really writing very well. Okay, should be a little more curved like that. Okay, so then this slight negative means that the electrons are more on the oxygen side because it has a greater pull or attraction for the electrons, and then therefore these electrons are not so much attracted to the hydrogen. Okay, so they are sharing, remember, these two electrons here, but they're not sharing equally. Okay, so you see how they created two poles, a negative pole and a positive pole. That's why water is considered polar. all right, polar. So remember, nonpolar is where all of the attachments are the same, and then therefore their dipoles will cancel out, making the overall molecule nonpolar. So then if something is polar, that means one of the attachments is different, okay? Is different. All right, so those are your basic properties of water that we just reviewed. So here's the shape of the water molecule if you were to make the model. This one on the left, okay, this one is called the ball and stick model. Okay, ball and stick model here. And then the one on the right, this is called the space-filled model. They're just two different pictures of the same thing. So space-filled allows you to see what it would look like when those atoms are occupying space. Okay? So notice this one has a 2 delta minus, and that's because we look at each bond individually. Okay? So between this O and this H, this one's the slight negative, that's the slight positive. Then between this bond here, that's the slight negative, that's the slight positive. That's why it's 2 delta minus. All right? And if you remember the bond angle for a bent shaped molecule, it's 105 degrees. Okay, this is reviewing the difference between solute and solvent. So remember, solute is what needs to be dissolved. Solvent is what does the dissolving. So water is the most common solvent. It's polar, and therefore it can dissolve just about anything. Okay? Remember when we did the Kool-Aid lab? So the solute would be the Kool-Aid, and then the water would be the solvent. All right, this is a great picture here. So let's take a look. This is a salt structure. This is sodium chloride. So remember, salt is ionic. You can see the structure, positive and negative ions, cations, anions, and see how they alternate, positive, negative, positive, negative. Okay, and that's why your ionic compounds are very, very strong. Then these are water molecules. All right, floating around. So your salt is being dissolved in water. Now notice what happens. Okay, notice the water molecules are attacking the ions, and the water molecules are pulling those ions away from the structure. Therefore, that's how your salt becomes dissolved. Okay, I'm going to zoom in here. So let's zoom in and take a look what's happening. All right, let's first take a look at this anion. So this anion, which is negative, look at the orientation of the water molecules. All right, what do you notice about the orientation of the water molecules? So the little white circles there, okay, these little white circles, those are the hydrogens. The red ones are oxygen atoms. Okay, so see how the water molecules are arranging themselves so that opposites attract. So the positive hydrogens are pointed towards the negative ion. All right, now if we go down here, look at the cation. Now look at the orientation of the water molecules. Notice it's the negatively charged side, the oxygen, right, that is pointed towards the positive ion. Opposites attract. Okay, so once again, notice the orientation of the water molecules when it is dissolving an ionic compound. All right, so you see how they are pulling the ions away from the structure, and that's how your salt becomes dissolved. Now it's separated into these charged particles. All right, so what this picture is doing is showing you once again how we can dissolve, or how water can dissolve also a polar molecule. All right, so here we have water coming in. Okay, this molecule is polar, right? Because of this right here, this OH that is being attached. All right, and that's polar. So notice once again how the water molecule is going to arrange itself when it dissolves a polar molecule. So the negative side of the oxygen is going to be attracted to the positive hydrogen on this polar molecule. Okay, and then this is going to get into our concept of like dissolves like. All right, so do you remember what like dissolves like means or what it refers to? Okay, so remember, as it says here, polar dissolves polar and also ionic compounds. Nonpolar dissolves nonpolar. So like dissolves like. All right, I'm also going to talk about electrolytes. So if you remember what electrolytes are, they are solutions that conduct electricity. Okay, they are solutions that conduct electricity. So we have what are called strong electrolytes, weak electrolytes, and non-electrolytes. So strong electrolytes conduct a lot of electricity. So these would be your, you should write this down, and here are some examples here. Your strong electrolytes would be your ionic compounds, and your strong acids, and strong bases. Okay? And then your weak electrolytes would be your weak acids and your weak bases. Also, it could be like a very slightly soluble ionic compound. Okay? Not an ionic compound that dissolves completely in water, but an ionic compound that like barely dissolves in water. Your non-electrolytes are going to be your molecular compounds. Okay, your molecular compounds. They do not conduct electricity at all because they are not separated into any charged particles. And we're going to take a look at a picture on the next slide. Now let's take a look at this picture. Let me zoom in so you can see this better. There we go. All right, so we have 3 different examples here. Let's take a look at this first example here. Notice as they expand to show you what the solution looks like, notice all of these ions are separated. Okay, they are free-flowing ions in solution. So this is an example of your ionic compound when it dissolves or completely dissolves in water. They completely separate into their ions. Therefore, look at the light bulb. Okay, it is very, very bright. Okay, this light bulb is very, very bright. So that is an indicator that that is a strong electrolyte. Okay, so this one is strong. So let's write that down. You should write that. So this one is, sorry, that is so bad. Let's erase. Okay, so strong electrolyte. Okay, then this middle one here, this is an example of a weak electrolyte. Okay, a weak electrolyte. See how only this particle right here is the only one that's separated. All the other particles are still together. Okay, so that's why it's very dim. It does conduct electricity, but not very much. All right, so let's label that one as being weak. And then let's take a look at the last picture. Notice these particles here. There are no charges on them at all. Okay? No charges. So therefore, it cannot conduct electricity. So then this would be classified as a non-electrolyte. Here's a list of your strong acids. So you will need to have these memorized, and it's really helpful so that you can determine which ones are going to be strong or weak electrolytes. All right, so the majority of these you memorized last year. The only new one that's added to your list is HClO4. Okay, So HNO3, which is nitric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, and this is, I believe, perchloric acid. Okay, so you need to make sure that you have all of those memorized. Here is a list of your strong bases. Remember, to recognize a strong base, you have to have a metal from group 1 or 2, except for magnesium, combined with hydroxide. All right, so if it is not a metal from group 1 or 2, then you know that it will be considered a weak base. Now we are going to go over the help sheet. So what we're going to focus on today, we're going to focus on precipitation reactions. All right, precipitation reactions. So hopefully you remember what a precipitate is. So a precipitate is the solid that forms when you are mixing, some chemicals together. So we did a precipitate lab last year, or in first year chemistry. So your precipitation reactions are going to be double replacement, okay? And once again, it's going to form an insoluble product. So an insoluble product means it does not dissolve very well in water. So you need to know your solubility rules. These are also stated in your book, all right? And it is a good idea to have these memorized, all right? So make sure you are familiar with them because they will help out a lot. All right, so remember your double replacement. It's like doing FOIL in math. So as you can see, the A and the D come together. So the outer ones come together. So A and the D come together. And then the inner ones come together. Okay, so you can see that the C and the B come together. All right. All right, so what you're going to do here, notice that the products are not listed. They are blank. Okay, remember these are double replacement reactions. So you have to do your FOIL, stick the outer ones together, and then stick the inner ones together. Okay, and when you do that, because you're making a new compound, you have to make sure that you are doing crisscross with the charges. Okay, you're doing crisscross with the charges. All right, and then you're going to balance the equation later. So then if you do your double replacement correctly, so then it'll be K and then NO3. Now it's just going to be 1 K and 1 nitrate. Hold on, let me move this. Because if you remember, K is +1. And then nitrate is -1, okay? So +1 and -1, so that's why I only needed one of each. All right, then the lead and the chlorine are going to come together. If you take a look here, okay, if nitrate is -1 and there's 2 of them, then that means that this lead is going to be +2, okay? So this is +2. This is -1, so you do your crisscross, right? So then it's PB with the +2, and then, erase that. And then it's being combined with Cl, that's -1. So remember the 2 comes down there. All right, so it's going to be PB Cl2. And then now what you need to do is balance the overall equation. All right, so if we balance this equation correctly, that means that we need, I'm going to use a different color here. We're going to need a 2 in front of here. Okay, a 2 in front of there. And then that will give us the 2 Ks. So you see by putting a 2 here, the reason why I put a 2 there was because there were 2 nitrates. So then I want to make those nitrates 2 by putting a 2 in the front. But that makes my K's 2, so I'm going to go to the other side and put a 2 there. Okay, by putting a 2 there, that balances out those. let's see, and I think everything looks good. Let's just double check. So 2 Ks, 2 Ks, 2 Cls, 2 Cls, 1 lead, 1 lead, 2 nitrates, and then the 2 there makes those nitrates too. All right, so now the equation is balanced. All right, so now what I want you to do is we need to look at our solubility rules above to find out if these products are aqueous or if one of them forms a solid. Okay, so notice this is combined with nitrate. Look at the rule. Rule number 1, most nitrate salts are soluble. Okay, soluble means it is dissolved in water. So then this is going to be labeled aqueous, AQ. So after this one, put AQ after it. AQ. Okay, and then look up the lead chloride. Okay, so then that would fall under here, okay, being combined with chloride. So most chloride salts are soluble, but not if it's combined with one of these. So it's combined with lead plus 2. Therefore, this is not soluble, so this is our solid. All right. Now what I want you to do is, now we write out the complete ionic equation. So if you remember how to do the complete ionic equation, this is where you are going to break down everything that is aqueous. Okay, so you will notice that this is aqueous, that's aqueous, and this is aqueous. So everything that is aqueous, you're going to go and separate it into its ions. The solid over here, you are going to keep together. So I like to box up the solid. It's a reminder to me that I am going to keep it together and I am not going to separate it. All right, so now what we are going to do is we're going to separate everything that is aqueous and then keep the solid together. All right, so 2 KCl, break it apart. The coefficient 2 you're going to carry throughout. So it's going to look like this. 2, and then that's a 2. And then it's going to be K, and you have to put its charges, okay? And then that's going to be added with 2 Cl minus, okay? So you can see how the 2, that coefficient 2, got multiplied through when we separated it. Okay, so we're going to keep going. So plus, and then separate the lead nitrate, it's Pb, and that has a plus 2 charge. And then that 2 on the outside of the nitrate, right there, is going to get moved to the front as a coefficient. Okay, so then it becomes 2 and then NO3 minus. All right, then the arrow, and we're going to keep going. I'm running out of room. Hopefully you wrote smaller than I did. Okay, so then the 2 nitrates here, 2 potassium nitrates, we're going to separate those. So it's going to look like this. 2 K plus, and then 2 nitrates. Okay, and then our lead chloride. Remember, we keep it together. I boxed it up. It is our solid. PbCl2. Once again, hopefully you wrote smaller than I did so you can fit everything on one line. All right. Okay, so now what we need to do is we can cross out what are the spectator ions. So that is what we have the same on the left and on the right hand side of the arrow. So you can go through each thing one at a time. So we have 2 K pluses here. We look on the other side of the arrow and look, we have 2 K pluses there. So those can cross out. So I'm going to cross those out. Okay, we keep going. 2 Cl minuses. Let's look on the right hand side of the arrow. Do we have 2 Cl minuses floating around by themselves? No, we don't, so we have to keep it. Okay? Keep going. Pb with the plus 2. On this side of the arrow, do I have a Pb plus 2 floating around by itself? No, I don't, so I have to keep it. All right, 2 nitrates, and then those 2 nitrates can cross out. And then I like to box up what is left so that I can see it easily. And then, so you can list what your spectator ions are. The spectator ions are the ones that you crossed out, okay? So the spectator ions are the ones that you crossed out. So you're going to list K plus and nitrate. Make sure you have the charges on them. The net ionic equation, go ahead and rewrite this nicely. It's what you boxed up, okay? I'm just going to write it down here at the bottom so you can see what it would look like when you write that nice and neat. So we have Pb with the +2 and 2Cl minus, and that gives us the PbCl2. You always should double check your answer. It should make sense, okay? And it should be balanced. All right, see how you have to have those two things come together to make that. All right, so make sure that equation makes sense. All right, so what I want you to do is go ahead and go on to number 2 and do this one on your own, and then we will check it in class. All right? Now, if we go ahead and take a look at the next page, all right, we're going to, this is the last problem that we're going to do today. This one right here. All right, stoichiometry of precipitation reactions. So this one I also want you to try on your own, and we will go over the answer in class. Okay, so I want you to read, you got to read the question yourself. Okay, you're going to have to write the equation yourself also. Okay, and then it is a stoichiometry problem. Okay, I'll give you a hint. So once you write out your equation, don't forget to balance it. Now look at this piece of information that's given to you. All right, and this is the hint that I will provide you as you're trying to work through this problem on your own. So you are given volume and molarity. If you have volume and molarity, what do you think you can find with that information? Well, you can find moles. Okay, remember your equation, molarity equals moles per liter. So you can convert the milliliters into liters. You already have the molarity given there. You plug that in there, and then you're able to solve for moles. Okay, so that is something that's very common type of information that would be provided for you. So when you see that, you should automatically think moles, all right? And then from there, you can do your stoichiometry, okay? So go ahead and work on those, and then in class, we will go over them, all right? Okay, so I will see you tomorrow. Bye.